Hello everybody, my name is Abdul Latif Bajigni. I will be the instructor for Electrical Circuit Concept online course. I will go over the syllabus very quick. As you see here, my full name, Dr. Abdul Latif Bajigni, office number 154, Mendel Building, office hours to be determined, and my email, bajignia@merrimack.edu. The course text, Applied Circuit Analysis, first edition. You can buy this book. The tentative schedule, we have to cover from chapter 1 to chapter 11, hopefully. The first chapter will talk about the basic concepts, and then second chapter will talk about resistance, about the third one about the energy, chapter 4 series circuits, chapter 5 parallel circuits, chapter 6 series parallel circuit, method of analysis, DC circuit theorem, capacitor, inductor. And if we have time, we will cover some aspects of AC voltage and current, and also the basic of the transformer. We will have two examinations, exam 1 and exam 2. Probably the time here, June 15 or June 30th. It's not the final time. I will send you the exact time for exam 1 and exam 2. Grading points, exam 1 worth 40 points, exam 2 40 points, laboratory experiments 20 points. Laboratory experiments consist of two parts. Part 1, hand calculation. Part 2, computer simulation using a software program called LT-SPICE. Each student is required to download a free version of the LT-SPICE 4. And here's the link that you can download it as soon as you start the course. Each student is required to submit a short lab report. Lab handouts will be provided by the instructor. Here is a quick course description. I will let you read the topics that I'm going to cover during this course. And here's some suggestions for meaningful learning process. Homework will not be graded. However, it is highly recommended that you complete all assignments in order to fully understand and comprehend the material. The examination will reflect the same material in the homework assignments. Power generation, transmission, and distribution. This schematic shows the power generation starts from the power station. This is the power station here. We have inside the building of the power station equipment such as the generator. This is the main part. And then we have a wire coming out from the generator, which is usually 3 wires, what they call it 3-phase. That 3 wires will be connected to a transformer. It's a power transformer, it's a very huge transformer, will convert the voltage produced by the generator to high voltage. They call it a step-up transformer. That high voltage will run through the transmission line, hanging on a large and huge towers. This is very high voltage. It reaches up to 1000 kilovolt. And then when the transmission line reaches the city or the skirts of the city, it will be stepped down. The voltage value goes down. And then we have another transformer that will step down the voltage and run the transmission line over poles. And then we have another one, another transformer, what you call it the distribution substation, where the voltage will be distributed to the customers. Either could be a commercial and industrial and business customers, or could be just the residential customers. The transformer here will reduce the voltage to a lower voltage to the commercial up to 460 volt or 380, depends on the country. And also the voltage here will be reduced to up to 120 to 240, that's in the United States. Here is the power generation voltage level. We can see here the generation part of the voltage will be ranging from 12.5 kilovolt to up to 25 kilovolt. And then we have step up transformer. It goes, or it ranges from 500, 345, 200, and 135 up to 1000 kilovolt. Depends on the application, depends on the customers, depends also on the countries. Then we have the step down transformer that will be at the substations that will produce or reduce the voltage down to 26K or 69K for some industrial, and also 113 kV and 4 kV for commercial, and 120 and 240 for the end users or the residential customers. Okay, we start now the chapter 1. We'll give an introduction, the basic concept of electricity. As we know that the nature of matters, everything in the universe is made up of matters. Matter is everything that occupies space or has mass. It can be found in the form of liquids, solids, and gases. However, it can also be described by color, taste, and hardness. An element is a substance that has been broken down to its purest form. These are over 100 elements, and some of them can be generated in laboratories. Some common examples of naturally occurring elements are iron, copper, gold, aluminum, carbon, and oxygen. If two or more of these elements are mixed together, a compound is generated. A molecule is the smallest part of a compound that still remains all the characteristics, that still retains all the characteristics of that compound. As an example, water is a compound. So if we boil the water will be converted into a steam, will be transferred to a steam. Now, the point before the water goes to the steam, that turnover is called a molecule. So a molecule actually it's amount, or it's a part of the water before it turns to steam. An atom is the smallest form of an element. It is derived from the Greek word meaning invisible. It is too small that is difficult to visualize, and we can see that in figure 1.4, where the atom shows the protons inside the nucleus, including the neutrons, and also we can see the protons that is in here in the outer orbit of the atom. To understand the mystery of electricity, and especially the characteristics of solid-state electrons, we must have a basic understanding of structure and phases that make up the atom. So atom consists of the nucleus in the center, and electron wire around this nucleus. So we have the nucleus, and around this nucleus there's electrons. Those electrons, they are revolving around its nucleus. The electron orbiting around the nucleus display a negative charge. The nucleus display a positive charge because it is composed of a positive charge protons and neutrally charged neither negative nor positive neutrons. The number of the electrons and protons that make up a particular atom are usually equal in numbers. So if we look to the electrons, it has a negative charge. Now, what is the meaning of the negative charge? A charge, basically, it's a small particle of an element. In this case, it's a small part of an atom, which is an electron. Proton also is a charge, or it's a particle. It's a small piece that makes the atom. Now, when that charge or when that particle has a force or an ability to attract or to oppose it's a similar charge, we call it a charge, which means it has a force. The number of the electrons and protons that make up a particular atom are usually equal in number. This equal number creates a cancel-in effect between the negative and the positive charge. The atom consists of electrons, protons, and neutrons. So this is as a summary, we have the atom as a particle. The atom consists of electrons that has or that have a negative charge or that have a force, and protons that have a force. But both of them, they are acting against each other in an opposite direction. So the net force that produced by the electrons and the protons of an atom is equal to 0. This means the atom itself, it has no charge. It has no charge, which means it has no force. So if there's two atoms next to each other, they are not attracting, neither push or repel each other. Ionization. When an electron leaves the outer orbit, the atom becomes ionized. So we have an atom. The atom itself, it has no charge. It's a neutral. It has no force, as we mentioned. Now, if we are able to take away one electron from the atom, then the atom becomes ion. And it becomes a positive ion. Why? Because the number of electrons, as we said, equal the number of the protons. So when we take one electron away, so the number of the protons exceed the number of electrons. In this case, the atom becomes an ion, and we don't call it anymore an atom because it lost one electron. That loss makes it a positive charge. Now that positive charge is actually represent or constitute the positive terminal of the power supply. So when we come to talk about the voltage supply or the source of the voltage or the power supply, so when we said a positive terminal of the voltage supply, we meant that terminal, it has millions and millions of those ionized positive ions. An ionized atom is electrically unbalanced, which means it becomes a positive or a negative, as we will see. Now, what is a positive ion? It is an atom that loses an electron from its outer orbit, as I mentioned. So when one electron leaves the atom, it becomes a positive ion. Now, what makes those electrons to leave? What is the mechanism? What is the force that will force that electron to leave its own orbit? There is many ways to do that. One way is the biochemical reaction. Another way is by the sunlight. Another way is by the heat. Another way is by mechanical force. The example of that is the microphone. All of these methods are used to ionize the atom or to produce the positive ion and the negative ion. The concept of a negative and positive ion is a key building block to understand electronic theory. Law of charges states that like charges repel each other and unlike charges attract each other. So if we bring two positive ions or two negative ions, they repel each other. If we bring one positive ion next to a positive ion, they attract each other. The coulomb is the unit of measuring of an amount of electricity. So this is the units that they use to measure how many electrons moving in the wire. So 1 coulomb represents approximately 6.24 multiplied by 10 to the power 18 electrons. So if we are able to have this number, that means we have 1 coulomb. Okay, what are the basic electrical circuit components? The basic electrical circuit, it consists of three main parts. If we lose one of them, if we don't have one of those parts, we cannot call it an electrical circuit. So these are the minimum. We might have more elements in the circuit, such as the switch, or a breaker, or a fuse, or an indicator, and so on. So the first part is the source of voltage, which is the electrical energy, such as the battery, or the DC power supply or AC power supply. The second one is the load, such as a lamp. And the third part is the conductor or the pad. So without having one of them, we don't have an actual electrical circuit. This circuit consists of a battery as the source of electrical energy, a lamp as the electrical load, and two wires as the conductors connecting the battery to the lamp. Now, what is the definition of the load? The load is an element that consumes energy, consumes electrical energy. So, for example, the lamp is a device that will convert an electrical energy into a light. If we replace the light bulb or the lamp by, for example, a fan, then the electrical energy will be converted into a motion, and so on. So if we have, for example, a dryer connected to the power supply, that dryer will convert the electrical energy into the heat. Or if we have a heater connected to the power supply, that heater will produce or will convert electrical energy into a heat. In the battery, a chemical reaction takes place that results in ionization. As I mentioned earlier, to produce the positive charge and the negative charge, which are constituting the two terminals of the power supply, the plus and the minus, by the chemical reaction. This ionization produces an excess of electrons or a negative charge and a depletion of electrons, positive charge. The battery has a positive terminal and a negative terminal. These two terminals are connected are connection points for the two conductors. Voltage, what is the definition of a voltage? Is the force behind electron flow. Also is called potential, electrical pressure, potential difference, or electromotive force, EMF. The volt or V is the electrical unit used to express the amount of electrical pressure present or the amount of electrical force produced by the chemical action inside the battery. Electrical voltage can be generated by ionization, that can be generated by force, such as heat, light, magnetism, chemical reaction, or mechanical pressure. So these are the sources of ionization. These are the sources of the voltage supply. So if we have the heat coming, this is how we measure, for example, the room temperature. And also if we have a light that coming from the sun, we can use the solar panel to convert the light of the sun into electricity. Magnetism, the best example of the magnetism is the generator that we use in the power station to generate electricity. Chemical reaction will show an example how to produce electricity or a positive ion and a negative ion using the chemical reaction. Or the mechanical pressure, and the best example, as I mentioned earlier, is the microphone. So when we speak to the microphone, we produce a pressure. That pressure will be converted into electricity. One of the examples of the microphone is the semiconductor material. There is special semiconductor material. If you put pressure on that material will become or will produce a positive charge and a negative charge. Now, what is the current? What is the definition of the current? The simplest definition of the current is the flow of the electrons. So if we are able to make the electrons to flow in the wire, that flow of the electron is called the electrical current. What is the unit? The unit is the ampere, is the amount of the electrons pass at any given point in 1 second. The current is expressed using the letter I. Okay, so what is the meaning of ampere? Okay, ampere is the name of a scientist. He contributed to science a lot. So they honor him giving the units of the name, the units of the current for his name. 1 ampere is equal to 1 coulomb. So that means if we have 1 ampere, that means we have 6.24 multiplied by 10 to power 18 electrons passing in the wire per second. So if we have that amount of electron passing per second in the wire, we are having 1 ampere. Okay, we have something also, another element, electrical element called a resistance. What is a resistance? A resistance is the opposition to the flow of electrons. We know that every element has a resistance, which means that when the current tries to flow through an element that has a resistance or has high resistance, those electrons that they try to pass from the conductor try to pass through the resistor. It will collide with these electrons, and then it will slow the passage of the number of the electrons. So they try to resist the number of the electron flowing in that resistance. And that's why we call it resistance, is trying to oppose the flow of the electrons. Resistance is measured in ohms, and the electrical symbol for ohm is the Greek letter omega. You see here, omega. Okay, now for the type of the conductors, we know that the electricity, as we mentioned, is the flow of the electron. So we need to provide a good conductor for the electron to flow. So a good conductor of electricity is anything that permits the free flow of the electron. So if we have a material that will allow the electrons to go with the minimum resistance or with the free resistance, that's called a good conductor. A poor conductor or insulator of electricity is a material that will not permit the free flow of the electrons. And that's why we have insulators around the wires that we use in our home. Okay, the cables that we use, or the wires that connect our computers to the supply, always will be covered by insulator, because to protect ourselves from getting shock. A semiconductor is a material that limits the flow free of electrons. It is neither a good conductor nor poor conductor of electricity. Semiconductor material are the very heart of modern electronic application. This type of semiconductor material are used in the semiconductor devices, such as diodes, such as amplifiers, just as transistors. Current, AC and DC. Now, since we define the current as the flow of the electrons, so there are two types of electrical current. A DC current, or direct current, only flows in one direction through an electrical circuit. So if we have a complete circuit, a power supply, path or wires or conductors, and the load. If we imagine that the current flow or the electrons is coming out from the positive of the terminal, goes through the wire, passes through the load, and goes back to the negative. And keep doing this constantly, continuously, this is called a DC current or a direct current. An example, a standard battery is an example which produces a DC current. The battery has a set of polarity, positive and negative terminals, and will produce an electric current in only one direction. AC, or alternative current, as its name implies, flow in both directions. First, it flows in one direction, and then it reverses its flow to the opposite direction. So, as you notice here in this figure here, we have the current flowing. Actually, this is what we call the conventional, or the electron theory, that the electrons flow from the negative polarity of the power supply, or the terminal of the power supply, coming out from the negative, goes through the load and go back to the positive terminal. And this will circulate continuously in one direction. Now, in the AC direction, or AC current, it doesn't matter where is the positive and negative, because this will be alternating, positive here, negative here, and then this become a positive and this terminal becomes a negative. So the current in one time will go in this direction, and then it's going to flip. Okay. Now, that is what we call 60 Hertz or 50 Hertz. So usually when you buy an equipment, you always focus on the Hertz, which means how many cycles. Okay. Hertz, again, it's a unit to measure the frequency, and in some countries there is 50 hertz, and in other countries they have 60 hertz. So 60 hertz means the current goes back and forth 60 times or 50 times per second. That's the meaning of the, so if the current goes this way, this is a half cycle, and then when you change direction, goes from that point to this point, this is one cycle. So in 50 hertz, this will be, this circulating or this cycling will happen 50 times or 60 times, depends on the country. So what is the difference between conventional current flow versus electronic flow theory? Long time ago, the scientists, they were thinking that the current will flow, or the electrons will flow from the positive terminal on the power supply through the wire, through the load to the other negative terminal. Then recently they discovered actually the other way around, and they call it the electron flow theory, which means that the current will flow from the negative through the load back to the positive terminal of the power supply. Electron theory, it is proven that current flow from negative to positive. Okay, now we begin talking about the resistance and Ohm's law, which is chapter 2. So as we mentioned in the chapter 1 about the resistance, which is the characteristics behavior of opposing the flow of electric charge, which is a current. So again, what is a current again? It's a flow of electrons. This opposition is due to the collision between electrons that make up the material. So when we have electrons that try to pass from the wire, from the terminal, through the wire, through the material, that material could be the resistance of the light bulb, could be the resistance of the heater, could be the resistance of the dryer, or the saw, or the drill. Whatever that load is, the material that this load made of, it has a resistance. Now, usually the resistance or the atoms of the resistance, or the atom of that material that make the resistance, consist of many more than 3 electrons in the outer orbit. Now, those 3 electrons, when the electron comes from the positive terminal, as I mentioned, it's going to collide. And this collision, it was going to reduce the number of the electrons that passes through the resistance. So when the resistance increases, the number of the electron passes, or the current, or the electrical charge will go down. This physical property or ability to resist current is known as resistance, and it is represented by symbol R, and it's measured in ohms. And the electrical symbol for ohms is the Greek letter omega. So the units are units ohms. We use either ohms or the Greek letter omega. Thus, the resistance R of any material with uniform cross-section area A and length L, as shown in figure below, is directly proportional to the length and inversely proportional to its cross-section area. So every material, regardless that material, we use it as a resistance or as a conductor, it has a resistance. That resistance, the mathematical formula, is equal to rho, R-U-H, this is the letter rho, multiplied by the length of the material, of the resistance or the wire, divided by the cross-section area. So rho is known as the resistivity of the material, and it is measured in ohm meter. The cross-section area of an element can be circular That element, as I said, could be copper, could be aluminum, could be iron, could be glass, could be rubber, either square or rectangular, and so on. For example, the cross-section area of a circle is A, which is the area equal to pi r square, or pi d over 2 square, or pi d square over 4, where r and d are the radius and diameter of the circle, respectively. Here is the a common material table for resistivity. As we see here, for the silver, it's very small. It's 1.64 10 to the minus 18. This is a good conductor. Copper also is a conductor. It's a little bit higher, but again, silver is expensive material. Copper is cheaper. Also, aluminum has a good resistivity, 2.8 10 to the minus. It's a little bit higher than the copper. Gold is very low. It's very low. So sometimes they use gold in the some of the circuits, the integrated circuit. And again, you go copper, germanium, silicon, paper, mica, glass, and Teflon. So these are the last four are insulators. These three here are semiconductor material. They used to make transistors. And then these four materials are used as conductors. Here's an example how to determine the resistance of a wire, of a material. So if we need to calculate the resistance of aluminum wire that is 2 meters long and of a circular cross-section with diameter of 1.5 meters. Now here, as a reminder, that the units has to be in meters. So we have to convert 1.5 to a meter. Okay, so we have to multiply this. The millimeter, it has 1 centimeter, it has 10 millimeter, and 1 meter, it has 100 centimeters. So we have to take the diameter here, we have to multiply the diameter by 10 to the minus 3 to convert it to meters, and then in squared, we divide by 4, we get this number, 1.767, 10 to the power minus 6. And then if we look to the table 2.2, the previous one, we can find that the resistivity rho is 2.8 10 to the minus 8. We go back to the example. We plug for rho, 2.8 to the minus 8, multiplied by the length L, which is 2 meters, divided by the cross-section area. We will find that the resistance R, it's 31.69 milliohms. It's very small resistance. That's why they pick the aluminum to be a conductor. Now for the practice problem, we will determine the resistance of an iron wire having a diameter of 2 millimeters and length of 20 meters. So again, we have to convert the D, 2 millimeters into meters by multiplying by 10 to the minus 3. And then we just follow exactly the same way as we did in example 2. We need to find A, so we plug for the D, which is 2 multiplied by 10 to the minus 3 squared over 4. And then we plug for the formula of the resistance R equal rho. Now we have to go to the table and look for the iron. If iron is not in this list, we can look for the iron through the Google. Now I'm going to use the board to solve the practice problems 2.1 and 2.2. So in this practice problem, we are asking to find the resistance of an iron wire of diameter 2 millimeters and length of 30 meters. So given information, we have D, which is 2 millimeters. We have to convert this to meters, so 10 to the minus 3 meters. And the length is 30 meters. Rho is 9.7, 10 to the minus 8 ohm meter. So we could get this information from the table provided in the notes. So now we need to find the resistance R. So from the formula, we have R equals to rho times L over the cross-section area. We know rho is 9.7, 10 to the minus 8, and the length is 30 meters. Divide by the area, which is, I should have the area. So area equals to 1/2 6, 10 to the minus 2, because it's a centimeter. So the area of the triangle, it's 1/2 times the base times the height, and multiply by the 4 times 10 to the minus 2. So converting centimeter to meters, this will become 12, 10 to the minus 4 meters. And so if you plug that value over here, it will be 12 multiplied 10 to the minus 4. I think I'm solving. Now I'm going to use the board to solve the practice problem 2.1 and practice problem 2.2. So in this problem, we need to find what is the resistance of an iron wire of the diameter 2 millimeters and the length of 30 meters. So in order to find this, we know that the resistance is equal to the rho, which is the resistivity, multiplied by the length of the wire over the cross-section area A. So we know that rho from the table is equal to 9.7, 10 to the minus 8 ohm meter. And then we have the length L is given as 30 meters. So the only thing we need to find is A, and A is pi, pi d squared over 4. So d is the diameter squared, so it will be pi over 4, and we have the diameter is 2 multiplied by 10 to the minus 3 to convert the meters into meters. So this will become 10 to the pi over pi 10 to the minus 6 meter. Okay, so this is the area. Now if we plug the area in this equation, we will determine R equal to the rho, which is 9.7, 10 to the minus 8. This is ohm meter, multiplied by the length, 30 meters, over by the cross-section area, is pi 10 to the minus 6 meters squared. So it's actually meters squared. So this will give us 9.927 ohm. Now, if you look to the book, he has a different answer. So I think this is the correct answer. Okay, now let's move to solve the practice the problem, practice problem number 2. So with the information we are given for the lid, we have to look to the table to determine the resistivity rho, 2.2 to the minus 7, And since the cross-section area is a triangle, so this is the formula of the area: 1/2 times the base times the height, and we have given 6 centimeter for the base and 4 centimeter for the height. We have to convert this into meters, multiply by 10 to the minus 2. So we end up having 12 10 to the minus 4. Now we are looking for the length. We are given R, so R is given as 1.25 10 to the minus 3 ohms. So we're given R, we're given A, we're given rho, we need to find L. So according to the formula for the resistance of a wire, would be rho times L over the cross-section area. And we're looking for the A, for the L, sorry. So if we do the cross multiply, RA equal to rho L. And if we divide by rho both sides, then we have L equal to R times A over rho. Okay, we are given R is 1.25 10 to the minus 3, and area, we determine area as 12 10 to the minus 4, 12 10 to the minus 4, and we have the rho from the table, 2.2 10 to the minus 7. Okay, and this one give us 6.82 meters. Again, the book has it as a centimeter, so the correct answer, actually, the units are meters here. So this will be probably the end of this tape.